Hello, and welcome to Napflix. Tonight, we are going to explore 100 facts about time travel. Not the Hollywood version with flickering lights and spinning dials. The real version, the one that is already happening, that has already been measured, that is quietly ticking away in the satellites above your head right now. The version where astronauts return to Earth younger than they should be. Where atomic clocks flown around the world come back disagreeing with the clocks that stayed behind. Where particles created in the upper atmosphere survive long enough to reach the ground only because time itself is stretching around them as they fall. And beyond the proven, the theoretical. The wormholes that Einstein's own equations permit. The black holes where a few hours for you could be centuries for everyone else. The paradoxes that have kept physicists awake for 100 years. The rotating universes where traveling into your own past is not just possible, but inevitable. The arrow of time that points in only one direction, and the deepest question of all, why? This is the science of time. What it is, how it bends, and whether it can ever be crossed. You do not need to stay awake for all of it. You do not need to remember any of it. Just let the words carry you. If your eyes grow heavy, let them close. If your mind begins to drift, let it drift. This is your time to rest. And if you enjoy what you hear, a like or subscribe helps others find their way here too. Now, let us begin. Time is not constant. It bends, it stretches, and it flows at different rates depending on where you are and how fast you are moving. This is not a theory waiting to be confirmed. It has been measured, tested, and verified thousands of times with some of the most precise instruments ever built. The clocks on satellites tick at a different rate from the clocks on the ground. The clocks on mountaintops tick at a different rate from the clocks in valleys. Particles moving at nearly the speed of light age more slowly than particles at rest. Time is not the rigid, universal metronome that Newton imagined. It is flexible, responsive, and shaped by the conditions of the universe around it. Everything we are going to explore tonight begins with this single, quietly revolutionary fact. Time is not what it seems. In 1905, a 26-year-old patent clerk in Bern, Switzerland, published a paper that would dismantle humanity's understanding of time. Albert Einstein's special theory of relativity showed that time is not absolute. It does not tick at the same rate for everyone. If two people are moving at different speeds, they experience time at different rates. The faster you move through space, the slower you move through time, relative to someone standing still. At everyday speeds, walking, driving, flying in a plane, the difference is so small that it is undetectable without extraordinarily precise instruments. But as speeds approach the speed of light, the effect becomes dramatic. At 90% of the speed of light, time for the traveler passes at roughly half the rate of time for the observer. At 99%, time slows to a seventh. The mathematics are clean, elegant, and have been confirmed in every experiment ever designed to test them. 10 years after special relativity, Einstein published his general theory of relativity, and time became stranger still. General relativity showed that gravity also affects time. The stronger the gravitational field, the slower time passes. A clock at the base of a skyscraper ticks fractionally slower than a clock on the roof, because the base is closer to the center of the Earth and experiences a slightly stronger gravitational pull. The difference is minuscule, billionths of a second over a human lifetime, but it is real and it has been measured. Gravity does not just pull objects toward each other. It warps the fabric of space-time itself, and when space-time warps, time bends with it. Near a massive object, like a planet or a star, time runs slower. Far from any mass, time runs faster. The universe does not have a single universal clock. It has an infinite number of clocks, each one ticking at its own rate, each one correct. In 1971, two physicists named Joseph Haffel and Richard Keating put Einstein's predictions to the most direct test imaginable. They bought seats on commercial airline flights, placed atomic clocks in the passenger cabin, and flew them around the world in both directions, eastward and westward. When the flying clocks were compared to identical clocks that had stayed on the ground at the United States Naval Observatory, they disagreed. The clocks that had flown eastward in the direction of the Earth's rotation had lost time. The clocks that had flown westward had gained time. The differences were measured in nanoseconds, billionths of a second, but they matched Einstein's predictions with remarkable precision. The Haffel-Keating experiment was not a thought experiment. It was not a mathematical proof. It was atomic clocks on aeroplanes checked against atomic clocks on the ground, showing that time had passed at different rates for objects that had been moving at different speeds. Time travel, in the most literal and modest sense, was demonstrated with commercial airline tickets and hand-carried laboratory equipment. The global positioning system, the network of satellites that tells your phone where you are, only works because its engineers understood and corrected for time dilation. The GPS system relies on extraordinarily precise timing. Each satellite broadcasts a signal that includes the exact time the signal was sent. Your phone receives signals from multiple satellites, compares the arrival times, and calculates your position based on the tiny differences. For this to work, the clocks on the satellites and the clocks on the ground must agree to within about 20 to 30 nanoseconds. But they do not naturally agree because two separate effects are pulling them in opposite directions. The satellites are moving at roughly 14,000 kilometers per hour relative to the ground, which makes their clocks tick slower due to velocity-based time dilation by about 7 microseconds per day. But the satellites are also 20,000 kilometers above the Earth, where gravity is weaker, which makes their clocks tick faster due to gravitational time dilation by about 45 microseconds per day. The net effect is that the satellite clocks run roughly 38 microseconds per day faster than clocks on the ground. Without correction, GPS positions would drift by roughly 10 kilometers per day. Every time you use a map on your phone, you are relying on engineers who understood that time passes at different rates in different places. Astronauts on the International Space Station age slightly less than people on the ground. The Russian cosmonaut, Gennady Padalka, holds the record for the most cumulative time spent in space by any human being, over 800, and 79 days across 5 missions. Because of the combination of his high orbital velocity and the slightly reduced gravity at the station's altitude, Padalka returned to Earth having aged roughly 22 milliseconds less than he would have if he had stayed on the ground. 22 milliseconds is not a lot. You would never notice it. But it is real, it is measurable, and in the strictest physical sense, Gennady Padalka has time-traveled 22 milliseconds into the future. He arrived in the present of everyone around him, having spent fractionally less time getting there. Muons provide one of the most elegant confirmations of time dilation in nature. Muons are subatomic particles created when cosmic rays from deep space collide with molecules in the upper atmosphere, roughly 15 kilometers above the Earth's surface. A muon has a very short lifespan, about 2.2 microseconds. Even traveling at nearly the speed of light, a muon should only be able to cover about 660 meters before it decays. It should never reach the ground. Yet muons arrive at the Earth's surface in enormous numbers. The explanation is time dilation. From the muon's perspective, It lives for 2.2 microseconds and travels a short distance. But from our perspective on the ground, the muon's internal clock is running slow because of its extreme speed. Its lifespan, as we observe it, is stretched by the Lorentz factor, giving it enough time to traverse the full 15 kilometers of atmosphere and reach our detectors. The muon does not know it is time traveling. It simply exists briefly in a universe where time bends around speed, and its arrival at the surface is proof, repeated trillions of times every day, that Einstein was right. Time passes measurably slower at sea level than at the top of a mountain. In 2010, scientists at the National Institute of Standards and Technology in the United States demonstrated this with aluminium-ion optical clocks, instruments so precise that they can detect differences in the rate of time caused by a height change of just 33 centimeters. They placed one clock on a table and raised another clock by 1/3 of a meter, and the higher clock ticked faster. The difference was about 90 billionths of a billionth of a second over a year, but the instruments could see it clearly. These clocks are now so sensitive that they could detect the gravitational time dilation between your head and your feet. Your head, being further from the center of the Earth, is aging fractionally faster than your feet right now, as you lie here. The difference over a lifetime is roughly 90 billionths of a second. It will never matter to you, but the universe is keeping track. Gravitational waves, ripples in the fabric of space-time itself, were detected for the first time on the 14th of September, 2015, by the Laser Interferometer Gravitational Wave Observatory, known as LIGO. The waves had been produced by two black holes, each roughly 30 times the mass of the Sun, spiraling into each other and merging roughly 1.3 billion light-years away. As the gravitational waves passed through LIGO's detectors, they stretched and compressed space-time by a tiny amount, roughly 1,000th of the diameter of a proton. The detection confirmed a prediction Einstein had made exactly 100 years earlier. Gravitational waves carry information about the distortion of time itself. As they pass through you, they are stretching and compressing time in one direction and then the other, by amounts so small that no human sense could ever detect them, but they are real. They pass through the Earth regularly, carrying echoes of the most violent events in the universe: colliding neutron stars, merging black holes, explosions that occurred billions of years ago, ripples in time that have been traveling across the cosmos ever since. A clock at the center of the Earth would tick measurably slower than a clock on the surface. The gravitational field is strongest at the center of a massive object, not at its surface, because at the center you are surrounded by mass in every direction. If you could somehow place a clock at the Earth's core, roughly 6,371 kilometers below your feet, it would run slightly but measurably slower than your wristwatch. The difference is tiny, roughly 1.1 parts in a billion, but it illustrates the same principle that governs time near black holes, near neutron stars, and near any concentration of mass. Gravity slows time. More gravity, slower time. The universe does not make exceptions. Particle accelerators routinely observe time dilation as a practical engineering reality. In the Large Hadron Collider at CERN, protons are accelerated to 99.9999991% of the speed of light. At this speed, the Lorentz factor is roughly 7,500, meaning that from the perspective of a stationary observer, the proton's internal clocks are running roughly 7,500 times slower than normal. Particles that would normally decay in microseconds survive long enough to complete millions of orbits around the 27-kilometer ring. The accelerator's design depends on time dilation being real and predictable. If Einstein had been wrong, the machine would not work. It works. The speed of light is the universal speed limit, roughly 299,792 kilometers per second, and nothing with mass can reach it. The reason is energy. As an object accelerates toward the speed of light, its relativistic mass increases, requiring more and more energy to accelerate further. As the speed approaches light speed, the energy required approaches infinity. No finite amount of energy can push a massive object to the speed of light. This is not an engineering limitation. It is a structural feature of the universe. The speed of light is not fast because photons are energetic. It is the rate at which causality itself propagates through space-time. It is the speed at which the universe updates itself, the maximum rate at which any influence, any signal, any effect can travel from one point to another. Everything in the universe obeys this limit. And because of this limit, time dilation exists. Time and space are not separate things. They are woven together into a single four-dimensional fabric called space-time. You cannot bend space without bending time. You cannot move through space without affecting your movement through time. This was Einstein's deepest insight, and it is the foundation on which everything else in tonight's exploration rests. In everyday life, time and space feel completely different. You can move freely in 3 dimensions of space, forward and backward, left and right, up and down. But you seem to move in only one direction through time, from past to future, at a rate you cannot control. In physics, however, time and space are aspects of the same structure. A massive object like the sun does not just curve space around it, it curves time as well. The curvature of space-time is what we experience as gravity, and it is this curvature, this bending of the fabric, that contains both space and time, that makes time travel not just possible, but inevitable. Every time you look at the sun, you are seeing it as it was 8 minutes and 20 seconds ago. Light travels at roughly 300,000 kilometers per second, but the sun is roughly 150 million kilometers away. The light that enters your eye at any given moment left the sun's surface over 8 minutes earlier. If the sun vanished at this instant, you would continue to see it shining for another 8 minutes and 20 seconds before the sky went dark. You would also continue to feel its gravitational pull for the same duration, because gravitational information also propagates at the speed of light. Looking at the sun is looking into the past. And this is true of everything you see, everything, without exception. The light from the lamp across the room left that lamp a few nanoseconds ago. The light from the moon left roughly 1.3 seconds ago. The further away the object, the deeper into the past you are seeing. The nearest star beyond the Sun, Proxima Centauri, is 4.24 light-years away. The light you see from it tonight left that star over 4 years ago. When that light began its journey, whatever was happening on Earth 4 years ago had not yet happened from the star's perspective. The light carries no knowledge of the present. It carries only the information of the moment it left. Every star in the night sky is a window into a different moment in the past. Some are showing you last decade, some are showing you last century, some are showing you the universe as it was before human civilization began. The sky is not a snapshot. It is a mosaic of different pasts, all arriving at your eyes simultaneously. Each one genuine, each one out of date. The Andromeda Galaxy is roughly 2.5 million light-years away, and on a clear, dark night, it is just barely visible to the naked eye as a faint smudge of light. That light has been traveling for 2.5 million years. When it left the Andromeda Galaxy, there were no modern humans anywhere on Earth. The species that would eventually become us was still millions of years from existence. That ancient light has crossed an almost inconceivable distance. And tonight, if you look in the right direction, it enters your eye and creates a signal in your visual cortex. You are receiving a message from 2.5 million years ago. The night sky is the deepest time machine available to anyone. The cosmic microwave background radiation is the oldest light in the universe. It was released roughly 380,000 years after the Big Bang, when the universe cooled enough for atoms to form and photons to travel freely through space for the first time. That light has been traveling for approximately 13.8 billion years. It fills every part of the sky in every direction, a faint glow of microwave radiation that is the afterimage of the universe's birth. When scientists observe the cosmic microwave background with instruments like the Planck satellite, they are looking at the oldest observable thing in the universe. They are seeing the universe as it was when it was less than 1,000th of its current age. It is the ultimate act of looking into the past, seeing the light from the first moment the universe became transparent. The twin paradox is not a paradox at all. It is a confirmed prediction of special relativity. If one twin boards a spacecraft, accelerates to a significant fraction of the speed of light, travels for some years, then decelerates, turns around and returns to Earth, that twin will be younger than the sibling who stayed behind. This is not a trick of perception. The traveling twin has genuinely experienced fewer seconds, fewer heartbeats, fewer moments of consciousness. The effect only becomes dramatic at extreme speeds. But it has been confirmed with particles, with atomic clocks on aircraft, and with every high-energy physics experiment ever conducted. The reason the thought experiment is called a paradox is that it seems to create a contradiction. From the traveler's perspective, it is the Earth that moved away and came back. So why should the traveler age less? The resolution is that the traveler accelerated and decelerated. The twin on Earth did not. Acceleration breaks the symmetry, and the twin who accelerated has objectively, physically, measurably experienced less time. There is something quietly poignant about this. The thought of returning home to find that the world has moved on without you, that the people you love have grown older while you remained almost the same. Time does not treat everyone equally, not even the people who love each other most. Time dilation has been measured with objects you can hold in your hand. In 2010, scientists at the National Institute of Standards and Technology demonstrated that a clock raised by just 33 centimeters, roughly the height of a briefcase standing on its end, ticked at a measurably different rate from a clock sitting on the table below it. The higher clock ran faster because it was fractionally further from the Earth's gravitational center. The difference was extraordinarily small, but the optical lattice clocks used in the experiment were precise enough to detect it. Time dilation is not something that only happens near black holes or aboard spacecraft. It is happening right now, everywhere, between every pair of points at different heights, between every pair of objects moving at different speeds. The universe is full of clocks ticking at different rates, and every single one of them is correct. The faster you move through space, the slower you move through time. And vice versa. You are always moving through space-time at the speed of light. This is one of the most counterintuitive and most beautiful results of special relativity. When you are standing still, not moving through space at all, you are moving through time at the maximum possible rate. All of your motion through space-time is directed along the time axis. As you begin moving through space, some of that motion is redirected from the time axis to the space axis. The faster you move through space, the less of your total motion remains in the time direction, and the slower time passes for you. At the speed of light, all of your motion through space-time is directed through space, and none is left for time. Time stops. This is why photons, which travel at the speed of light, experience no time at all. A photon emitted from a star billions of light-years away arrives at your eye having experienced zero elapsed time. From the photon's perspective, its emission and its absorption happens simultaneously. Billions of years for you, an instant for the light. Traveling forward in time is not only possible, it is something we do constantly. Every astronaut who has orbited the Earth has traveled into the future by a tiny amount. Every passenger on every aeroplane has experienced fractionally less time than the people who stayed on the ground. Every person standing on a mountaintop is aging fractionally faster than the people in the valley below. We are all time travelers, moving forward at slightly different rates depending on our speed and our proximity to massive objects. The differences are too small to notice in everyday life, but they are real, they are cumulative, and they have been measured with extraordinary precision. Forward time travel is not speculative. It is physics. It is happening to you right now. Traveling backward in time is where the physics becomes uncertain. Nothing in Einstein's equations explicitly forbids it. The equations of general relativity are symmetric with respect to time. They work equally well whether time runs forward or backward. Several solutions to Einstein's field equations describe spacetimes in which backward time travel is theoretically possible. Rotating universes, the interiors of certain black holes, and spacetimes containing wormholes. But no mechanism for traveling into the past has ever been demonstrated, and there are strong theoretical reasons to suspect it may be impossible. Whether the past is genuinely unreachable or merely unreached is one of the most profound open questions in physics. The Lorentz factor is the mathematical expression that governs how much time dilation occurs at a given speed. It is defined as 1 divided by the square root of 1 minus the square of the velocity divided by the square of the speed of light. At everyday speeds, the Lorentz factor is so close to 1 that time dilation is negligible. At 50% of the speed of light, it is roughly 1.15, meaning time runs about 15% slower. At 90%, it is roughly 2.3. At 99%, it is roughly 7.1. At 99.99%, it is roughly 70.7. And as the velocity approaches the speed of light, the Lorentz factor approaches infinity. This is not a gradual curve. It is an exponential explosion. The closer you get to light speed, the more dramatically time slows, and the more energy is required to accelerate even slightly further. The universe does not gently discourage you from reaching the speed of light. It makes it infinitely expensive. Proper time is the time measured by a clock that travels with you, and it is always the shortest time between any two events. This is one of the most fundamental results of special relativity. If you travel from Earth to a distant star and back, the time you experience on your ship, your proper time, will always be less than the time experienced by someone who stayed on Earth. Every other observer, everyone who followed a different path through space-time, will measure a longer duration between your departure and your return. This is not because your clock is broken. It is because the geometry of space-time rewards the traveler with less elapsed time. The shortest path through space-time is the one that involves the most change in velocity, the most curvature, the most acceleration, and the reward for taking that path is arriving in the future having spent less time getting there. Wormholes are theoretical tunnels through space-time that connect two distant points, and they are permitted by Einstein's equations. The concept was first described mathematically by Einstein and the physicist Nathan Rosen in 1935, which is why wormholes are also called Einstein-Rosen bridges. Think of space-time as a sheet of paper. 2 points on that sheet might be far apart if you travel across the surface. But if you fold the paper so that those 2 points are directly opposite each other, you could poke a hole through both layers and travel from one to the other in almost no distance at all. That is a wormhole. A shortcut through the fabric of the universe. General relativity does not rule them out. Whether they actually exist in nature is another question entirely, and a much harder one. But the fact that the most successful theory of gravity ever written permits their existence is itself remarkable. The equations that describe reality allow for tunnels through it. To keep a wormhole open long enough to travel through, you would need something called exotic matter, a hypothetical substance with negative energy density. Ordinary matter has positive energy. It pulls space-time inward. Exotic matter, if it exists, would push space-time outward, propping the tunnel open the way a doorstop keeps a door from closing. Without exotic matter, a wormhole would collapse almost instantly, pinching shut before anything could pass through. Quantum mechanics allows for tiny, fleeting violations of positive energy in the form of the Casimir effect and quantum vacuum fluctuations. But whether these effects could be harnessed at the scale required to stabilize a traversable wormhole is unknown. Exotic matter in the quantities and configurations needed has not been confirmed to exist. The wormhole remains, for now, a mathematical possibility waiting for the physics to catch up. In 1988, the physicist Kip Thorne, who would later win the Nobel Prize for his work on gravitational waves, published a paper exploring whether a traversable wormhole could be used as a time machine. His conclusion was nuanced and careful. If a wormhole could be built and stabilized, and if one end of the wormhole were accelerated to a high speed and then brought back, the two ends would have aged differently due to velocity-based time dilation. One end would be in the future relative to the other. A traveler entering the younger end would emerge from the older end at an earlier time. In principle, the wormhole would connect two different moments. The image is irresistible. A doorway in an ordinary room, and through it, not another room, but another year. The air on the other side smelling different. The sky a slightly different shade of blue. Thorne's paper did not claim this was practical. It claimed it was not forbidden by known physics. And that distinction between impossible and not yet ruled out is where much of modern theoretical physics lives. Kurt Gödel, one of the greatest logicians in the history of mathematics, found a solution to Einstein's equations that described a universe where time travel into the past would be inevitable. Gödel had already achieved mathematical immortality in his 20s by proving the incompleteness theorems, showing that any sufficiently complex mathematical system must contain truths that cannot be proven within that system. In 1949, he turned his attention to general relativity and discovered a solution describing a rotating universe. A universe in which the fabric of space-time itself spins. In such a universe, certain paths through space-time, called closed time-like curves, would loop back on themselves. A traveler following one of these paths would eventually return to the same point in space and time from which they departed. When Gödel presented this to Einstein, Einstein was deeply unsettled. His own equations admitted solutions that allowed time travel. Our universe does not appear to be a Gödel universe. It does not rotate in the way his solution requires. But the existence of that solution in the mathematics suggests something profound. The equations that describe our physical reality do not, in and of themselves, forbid time travel into the past. Closed time-like curves are paths through space-time that loop back on themselves. A traveler following such a path would move continuously forward through their own experience, never reversing, never stopping, and yet would arrive back at the same point in space and time from which they departed. They would meet their past self. They would exist at the same moment twice. Closed time-like curves appear in several solutions to Einstein's field equations, including Gödel's rotating universe, the interior of rotating black holes, and certain spacetimes containing cosmic strings. Whether any of these solutions correspond to conditions that actually exist or could be created in our universe remains an open question. But their presence in the mathematics is a persistent, tantalizing hint that the structure of space-time may be stranger than our experience of it suggests. The Tipler cylinder is a theoretical time machine proposed by the physicist Frank Tipler in 1974. It consists of an infinitely long, rapidly rotating cylinder of ultra-dense matter. As the cylinder spins, it drags space-time around it in a phenomenon called frame dragging, predicted by general relativity and confirmed in experiments like Gravity Probe B. If the cylinder rotates fast enough, the dragged space-time would contain closed time-like curves, paths that loop backward in time. A spacecraft flying a carefully calculated trajectory around the cylinder could, in principle, travel into its own past. The catch, beyond the obvious engineering challenges, is that Tipler's original solution requires the cylinder to be infinitely long. A finite cylinder, some calculations suggest, would not produce closed, time-like curves. Whether a modified version could work is still debated. The Tipler cylinder is not a blueprint. It is a thought experiment that shows, once again, that Einstein's equations permit scenarios that Einstein himself might have found deeply uncomfortable. Cosmic strings are hypothetical, one-dimensional defects in space-time that may have formed during phase transitions in the very early universe, in the same way that cracks form in ice as water freezes. If they exist, cosmic strings would be extraordinarily thin, far thinner than an atom, but immensely dense, with a single centimeter of cosmic string potentially weighing as much as a mountain. In 1991, the physicist J. Richard Gott showed that if two cosmic strings passed each other at sufficiently high speeds, the warped space-time around them could create closed, time-like curves. A spacecraft flying a carefully timed loop around the two passing strings could, in theory, arrive back at its starting point before it left. No cosmic string has ever been detected. Their existence remains hypothetical, but the mathematics is sound, and the possibility they represent is another entry in the growing catalogue of spacetimes where backward time travel is not forbidden. The Alcubierre warp drive is a theoretical solution to Einstein's equations that would allow a spacecraft to travel faster than light without violating relativity. Proposed by the Mexican physicist Miguel Alcubierre in 1994, the drive works not by accelerating the spacecraft itself, but by manipulating the space-time around it. Space-time in front of the craft would be compressed, bringing distant points closer. Space-time behind the craft would be expanded, pushing the departure point further away. The spacecraft itself would sit in a bubble of flat space-time, stationary relative to its local environment, while the bubble moves through the universe at any speed, including speeds greater than light. Inside the bubble, no law of physics is violated, The passengers feel no acceleration. Time passes normally. But relative to the rest of the universe, the bubble and everything inside it can cover vast distances in arbitrarily short times. Like wormholes, the Alcubierre drive requires exotic matter with negative energy density, and the quantities originally calculated were impossibly large, more energy than exists in the observable universe. More recent refinements have reduced the energy requirements dramatically, though they remain far beyond anything achievable with current technology. The warp drive remains theoretical. But it is theoretical within the framework of general relativity, not outside it. Einstein's equations allow it. The universe, as described by our best physics, permits faster-than-light travel. Whether nature permits it in practice is a question we cannot yet answer. Black holes are the most extreme time machines in the universe. Near the event horizon of a black hole, the boundary beyond which nothing can escape, gravitational time dilation becomes so severe that time for a nearby traveler almost stops relative to a distant observer. A spacecraft hovering just above the event horizon of a supermassive black hole, the kind that sits at the center of most large galaxies, would experience time passing normally. The crew would eat, sleep, think, and speak with the full richness of consciousness. But to an observer watching from far away, the crew would appear to be moving in extreme slow motion. A few hours aboard the ship might correspond to decades, centuries, or even millennia in the outside universe. If the ship could somehow pull away and return to the rest of the cosmos, the crew would find themselves in the distant future, having aged only days. At the event horizon of a black hole, time dilation becomes infinite from the perspective of a distant observer. If you watched someone falling toward a black hole from a safe distance, you would never see them cross the event horizon. Their image would slow, redden, and dim. But it would never disappear entirely. They would appear to freeze at the threshold, their last moments stretched toward eternity. From their own perspective, they would feel nothing unusual at the moment of crossing. The event horizon is not a physical surface. It is simply the point of no return, the invisible boundary beyond which escape becomes impossible. The falling person would continue to experience time normally, falling inward, thinking, breathing, observing, but they would never be able to communicate with the outside universe again. They would have crossed into a region of space-time from which no signal, no light, no information of any kind can return. A person falling into a supermassive black hole would not be torn apart at the event horizon. Smaller black holes produce extreme tidal forces near their event horizons, stretching anything that approaches into a thin stream of matter in a process colorfully called spaghettification. But supermassive black holes, those containing millions or billions of solar masses, have event horizons so large that the tidal forces at the boundary are gentle. A person falling through the event horizon of a supermassive black hole could, in principle, survive the crossing and continue falling inward, experiencing time and space in ways that our current physics cannot fully describe. Inside a rotating black hole, called a Kerr black hole, after the physicist Roy Kerr, who described it mathematically in 1963, the structure of space-time becomes extraordinary. Instead of a point singularity, a Kerr black hole contains a ring singularity, a ring of infinite density rather than a point. The mathematics of general relativity permits passage through the center of this ring into regions of space-time where closed time-like curves exist. In principle, a traveler who survived the journey could travel backward in time. Most physicists believe this mathematical possibility does not correspond to physical reality. The interior of a real rotating black hole is likely far more chaotic and unstable than the idealized Kerr solution suggests. But the mathematics permits it, and the mathematics of general relativity has been right about everything else. The Penrose diagram is a way of mapping the entire causal structure of a space-time onto a finite sheet of paper. Named after the mathematician Roger Penrose, these diagrams compress infinite distances and infinite times into a readable chart that shows which events can influence which other events. The Penrose diagrams for certain black holes, particularly rotating and charged black holes, show structures that include connections to other universes or other regions of space-time. Whether these connections are physically real or merely mathematical artifacts is one of the great open questions in theoretical physics. But the diagrams reveal something important about the structure of space-time. It is richer, more connected, and more surprising than the 3 dimensions of space and 1 dimension of time that we experience in everyday life. Stephen Hawking's chronology protection conjecture proposes that the laws of physics conspire to prevent time travel into the past. Hawking could not prove this conjecture, but he felt strongly that it was true, and his reasoning was intuitive and elegant. He pointed out that if time travel into the past were possible, the universe would already be full of time travelers. History would be crowded with anachronisms. The absence of visitors from the future was, to Hawking, suggestive evidence that the past cannot be visited. Either the past is protected by some physical law we have not yet identified, or something about the nature of causality makes backward time travel genuinely impossible. The conjecture remains unproven. It is a bet about the structure of reality, placed by one of the greatest physicists who ever lived. Hawking once hosted a party for time travelers. He set up champagne, prepared food, and decorated a room at the University of Cambridge. Then, after the party was over, he published the invitation. The idea was simple. If time travel into the past is possible, someone from the future might receive the invitation and attend. No one came. Hawking sat alone in the room with glasses of champagne and an empty table. He described the experiment as evidence, though not proof, that backward time travel is impossible. The party went unattended. But of course, the experiment proves nothing definitive. Perhaps time travelers were uninterested. Perhaps attending would have caused a paradox. Perhaps the future does not contain time machines. The image, though, is quietly wonderful. A man in a wheelchair surrounded by champagne, waiting for guests who had not yet been born. The Cauchy horizon inside a rotating black hole is the boundary beyond which the future becomes unpredictable. Beyond the event horizon, the laws of physics still determine what happens next. Beyond the Cauchy horizon, they do not. In the mathematical description of a Kerr black hole, the Cauchy horizon marks the edge of the region, where closed time-like curves begin to appear. Many physicists believe the Cauchy horizon is unstable, that quantum effects and the accumulation of infalling radiation would cause it to collapse into a singularity before any traveler could cross it. This is called the strong cosmic censorship conjecture, and it is another of those elegant, unproven ideas that may protect the universe from the consequences of its own mathematics. If the Cauchy horizon does collapse, the time travel regions inside rotating black holes would be inaccessible. If it does not, the universe has a back door that leads to the past. Quantum mechanics and general relativity are the 2 most successful theories in the history of physics, and they are fundamentally incompatible with each other. General relativity describes gravity as the curvature of space-time and works beautifully at large scales. Planets, stars, galaxies, black holes. Quantum mechanics describes the behavior of matter and energy at the smallest scales: atoms, photons, quarks. Each theory has been confirmed by thousands of experiments. Each makes predictions of astonishing accuracy, but they cannot both be correct as currently formulated. Where they conflict most acutely is at the singularity inside a black hole, where general relativity predicts infinite density and quantum mechanics predicts that infinities should not exist. Resolving this conflict, unifying quantum mechanics and general relativity into a single coherent theory of quantum gravity, is the great unfinished project of modern physics. And it may reveal the deepest truth about the nature of time. Some approaches to quantum gravity suggest that at the Planck scale, roughly 10 to the power of minus 35 meters, space-time itself breaks down. At this unimaginably tiny scale, space-time is no longer the smooth, continuous fabric described by general relativity. It becomes something else, a quantum foam of fluctuating geometry, a granular structure, or perhaps something that has no spatial or temporal character at all. If space-time is emergent, arising from something more fundamental at the Planck scale, then time as we experience it may not be a basic feature of reality. It may be a large-scale approximation, a useful description that works perfectly well at human scales but dissolves into something unrecognizable at the deepest level of nature. Planck time is roughly 5.4 times 10 to the power of minus 44 seconds. It is the smallest meaningful unit of time, the duration below which our current physics cannot describe what happens. It is the time it takes light to travel one Planck length. Below the Planck time, the very concept of before and after may lose its meaning. The equations of quantum mechanics and general relativity both break down. No experiment has ever probed timescales this short, and it is unclear whether any experiment ever could. Planck time marks the boundary of our knowledge. Beyond it, time may not exist in any form we would recognize. Richard Feynman, one of the most brilliant and intuitive physicists of the 20th century, proposed an idea so strange that it still unsettles people who hear it for the first time. He suggested that a positron, the antimatter counterpart of an electron, could be mathematically described as an electron traveling backward in time. In Feynman diagrams, the visual tools physicists use to calculate the behavior of subatomic particles, an antiparticle is represented by a line pointing backward along the time axis. The mathematics works perfectly. Every interaction involving antimatter can be described with complete accuracy as the same interaction involving the corresponding particle moving in the opposite direction through time. This does not mean that antimatter is literally traveling backward in time in any experiential sense. But it means that the mathematics of particle physics does not distinguish between a particle moving forward and an antiparticle moving backward. Time at the quantum level has a symmetry that our everyday experience hides completely. The delayed choice quantum eraser experiment is one of the most unsettling results in quantum physics. In the experiment, a photon's behavior appears to be influenced by a measurement made after the photon has already completed its journey. The photon passes through a double slit, creating an interference pattern consistent with wave-like behavior. But if information about which slit the photon passed through is recorded, the interference pattern disappears. Here is the disturbing part. The recording can be made after the photon has hit the detector. The decision to record or erase the which path information appears to retroactively determine whether the photon behaved as a wave or a particle. The experiment does not allow information to be sent into the past. It cannot be used for communication or for changing history. But it suggests that the relationship between cause and effect at the quantum level is more subtle and more strange than our intuitions allow. The block universe theory holds that past, present, and future all exist simultaneously. This view arises naturally from Einstein's equations. In the block universe, time is simply another dimension of space-time, not fundamentally different from the three dimensions of space. Just as all locations in space exist simultaneously, all moments in time exist simultaneously. The past is not gone. It is simply in a different location along the time dimension. The future is not empty. It is already there. The sensation of moving through time, the feeling that the present is special and that the past has vanished, is, in this view, an illusion created by consciousness. Many physicists find this view deeply strange. It seems to challenge free will, change, and progress. But others find it comforting. Every moment you have ever lived still exists, laid out in the fabric of space-time. The people you have lost are not gone. They are simply elsewhere along the time dimension, present in a way you cannot access, but present nonetheless. If the block universe is correct, then time does not flow. Nothing moves from past to future. All moments exist, fixed and complete, like frames of a film laid out on a table. The experience of time passing, the sense that the present is advancing into the future while the past recedes, is something that consciousness creates as it encounters each moment in sequence. Some philosophers call this the moving spotlight theory, imagining consciousness as a light that illuminates one frame at a time while the entire film exists in the dark. Whether this is the correct description of reality is one of the deepest questions in both physics and philosophy. The block universe is consistent with Einstein's equations, but whether Einstein's equations capture the full truth about time or only a useful approximation is something we do not yet know. The many worlds interpretation of quantum mechanics proposed by Hugh Everett III in 1957 suggests that every quantum event causes the universe to split into branches. Each possible outcome of a quantum measurement is realized in a separate, equally real universe. The result is a vast, continuously branching tree of parallel timelines, each one containing a complete and self-consistent history. In this framework, time travel into the past would not create paradoxes because the traveler would arrive not in their own past, but in a parallel branch of the multiverse. The grandfather paradox dissolves. You could go back and prevent your grandparents from meeting, but you would be doing so in a different universe. Your original timeline remains intact. The many worlds interpretation is not universally accepted. It is one of several competing interpretations of quantum mechanics. But it is taken seriously by many physicists, and it offers an elegant resolution to the logical problems that backward time travel creates. David Deutsch, the physicist who pioneered the theory of quantum computation, proposed in 1991 that time travel paradoxes could be resolved if the universe follows quantum mechanical rules at every scale. In Deutsch's framework, a time traveler who goes back and tries to change the past would find that quantum mechanics ensures consistency. The traveler might arrive in a parallel branch of the multiverse where the past is slightly different, or the quantum probabilities might conspire to prevent the paradox from forming. Deutsch's model uses the mathematics of quantum information theory to show that self-consistent time travel is possible within a many worlds framework, without requiring any violations of physical law. It is one of the most rigorous attempts to make backward time travel compatible with known physics, and it comes from a man whose contributions to quantum computing alone would secure his place in the history of science. The grandfather paradox is the most famous puzzle in time travel, and it goes like this. Imagine you build a machine that allows you to travel back in time. You travel back to a period before your grandfather met your grandmother. Through some accident or misfortune, you prevent them from ever meeting. If they never met, your parents were never born. If your parents were never born, you were never born. And if you were never born, you never built the machine, never traveled back in time, and never prevented your grandparents from meeting. In which case, they did meet, and your parents were born, and you were born, and you built the machine and you traveled back, and so on, around and around, with no resolution. The paradox has occupied physicists and philosophers for decades. It does not prove that time travel is impossible. It proves that if time travel is possible, something must prevent paradoxes from forming. The question is, what? The bootstrap paradox is subtler and in some ways stranger. Imagine you travel back in time and give William Shakespeare a complete copy of his own, collected works before he has written them. Shakespeare copies them out in his own hand and publishes them. The plays exist. They are performed, celebrated, and preserved for centuries. You find them in the future, take them back, and give them to Shakespeare. The question is, who wrote them? You did not write them. Shakespeare did not write them. The information has no origin. It exists in a closed loop created by nothing, sustained by the loop itself. The bootstrap paradox does not involve any logical contradiction in the way the grandfather paradox does. The timeline is consistent. Nothing is impossible within it. But the information comes from nowhere. And that feels deeply wrong. It violates our intuition about causality, the idea that everything must have a cause. In a universe that permits time travel, causality may be more flexible than we assumed. The Novikov self-consistency principle proposes a resolution to time travel paradoxes that is both elegant and unsettling. Named after the Russian physicist Igor Novikov, it states that if time travel is possible, then only self-consistent events can occur. You could travel to the past, but only in ways that are already part of the timeline as it happened. If you went back to prevent your grandparents from meeting, something would always stop you. You would arrive at the wrong moment or make a mistake or change your mind. Not because of any external force, but because the universe is self-consistent. Your interference was never going to work because it never did work. Because the meeting happened. Because you were born. The principle does not require a cosmic enforcer. It simply states that contradictions cannot occur. The past happened the way it happened, and any time travel that occurs was always part of what happened. This turns the time traveler from a free agent into a character in a story that has already been written, a story that includes their arrival from the future as one of its fixed events. The butterfly effect, from chaos theory, suggests that even the smallest change to the past could cascade into enormous and unpredictable changes to the present. The term was coined by the meteorologist Edward Lorenz, who demonstrated in 1961 that tiny differences in initial conditions, differences as small as a butterfly flapping its wings, could lead to completely different weather patterns weeks later. Applied to time travel, the butterfly effect means that even the most careful visitor to the past would be incapable of leaving things unchanged. The air displaced by their breathing, the bacteria on their skin, the light reflected from their clothing, all of these would interact with the environment in ways that would compound over time. By the time the traveler returned to the present, the world might be unrecognizably different. The butterfly effect does not prove that time travel is impossible. but it suggests that even if it were possible, traveling to the past without changing it would be effectively impossible. The past is not a museum you can visit. It is a living system where everything is connected to everything else. H.G. Wells published The Time Machine in 1895, and in doing so, he invented not just a story, but a concept that had never existed before. Before Wells, stories about visiting other times involved magic, dreams, or divine intervention. Characters were sent to the past by angels or to the future by enchantment. Time was something that happened to people. Wells changed that. His time. Traveller was an inventor who sat in a workshop and built a machine. He pulled a lever, and the world outside blurred, seasons flickering past like turning pages, years dissolving into centuries. Wells understood before Einstein had written a single equation that time might be a dimension, something like height or width or depth, something that could, in principle, be traversed. He called it the fourth dimension. Every time travel story told since, every film and television series and novel that involves a machine or a portal or a device owes something to that young man sitting at his writing desk in the 1890s. The phrase time machine was coined by H.G. Wells. It did not exist before his novel. The words had been used separately, of course, but the compound phrase, meaning a device specifically designed to transport a person to a different point in time, was Wells's invention. It entered the English language so completely and so quickly that most people assume it has always existed. It has not. It is 131 years old, and it was created by a novelist, not a physicist. The science caught up later, but the language came first, and the language shaped the science. When physicists discuss theoretical mechanisms for moving through time, they reach for Wells's phrase without thinking. The vocabulary of time travel was invented by a storyteller, and it has been borrowed by science ever since. Charles Dickens's A Christmas Carol, published in 1843, is one of the earliest time travel narratives in English literature. Ebenezer Scrooge is visited by three spirits who transport him to his own past, his present, and his future. He watches scenes from his childhood. He observes events happening simultaneously in different parts of London. He witnesses his own death and its aftermath. Scrooge does not control the journey. He is a passenger carried by forces greater than himself. But the structure of the story, the movement of a character through different points in time to witness events and return changed, is the architecture of time travel fiction. Dickens did not call it time travel. The concept did not yet have a name, but the shape was already there, 52 years before Wells built his machine. The concept of time zones was invented in the 19th century because of railways. Before standardized time, every town set its clocks by the local position of the sun. Noon was when the sun was highest, and this varied by several minutes from one town to the next. This was perfectly adequate when the fastest mode of transport was a horse. But when railways connected distant towns with schedules measured in minutes, the lack of a common time became dangerous. Trains collided because the clocks at two stations disagreed. Passengers missed connections because the time in the departure city was different from the time in the arrival city. In 1847, British Railways adopted Greenwich Mean Time as a standard. In 1884, an international conference in Washington divided the world into 24 time zones, each 1 hour apart. The invention of time zones was not a scientific discovery. It was a practical response to the fact that speed had made the old relationship between humans and time unworkable. We did not change time. We changed how we agreed to measure it. The international date line runs roughly along the 181st meridian in the Pacific Ocean, and crossing it is the closest thing to time travel that requires no physics at all. If you fly westward across the line, you skip forward a day. Tuesday becomes Wednesday. If you fly eastward, you go back a day. Wednesday becomes Tuesday. The line exists because the Earth is round, and time zones must begin and end somewhere. The 181st meridian was chosen because it passes mostly through open ocean, minimizing the number of inhabited places that would be split between two different calendar dates. But the line is not straight. It zigzags to avoid cutting through island nations, creating odd situations where neighboring islands can be 25 hours apart, despite being visible to each other. The international date line is a human invention, an arbitrary line drawn on a map to make the mathematics of timekeeping work on a sphere. But crossing it feels, for a moment, like something more. Leap seconds are occasionally added to coordinated universal time to keep atomic clocks synchronized with the Earth's rotation. Atomic clocks are extraordinarily precise, losing or gaining only about 1 second over 300 million years. The Earth is less reliable. Its rotation is gradually slowing, primarily due to tidal interactions with the Moon, and the length of the day varies unpredictably due to shifts in the Earth's internal mass distribution, changes in atmospheric wind patterns, and even the redistribution of water from ice caps to oceans. When the difference between atomic time and astronomical time approaches 1 second, a leap second is inserted. Since the practice began in 1972, 27 leap seconds have been added. Each one is a quiet acknowledgement that human time and cosmic time do not quite agree, and that the most precise timekeeping in history must still occasionally defer to the irregular spinning of a 4.5 billion-year-old rock. The Antikythera mechanism, recovered from a Greek shipwreck dating to roughly 100 BC, is the most sophisticated timekeeping and astronomical prediction device of the ancient world. It is a complex assembly of bronze gears, roughly the size of a shoebox, that could predict the positions of the sun, moon, and planets, the phases of the moon, the timing of eclipses, and the dates of the Olympic Games. Nothing remotely as complex would be built again for over 1,000 years. When it was first recovered from the seabed in 1901, its purpose was not understood. It looked like a corroded lump of metal. It took decades of X-ray imaging and careful reconstruction to reveal the intricate gear train inside. The mechanism demonstrates that ancient Greek engineers had a sophisticated understanding of astronomical cycles and the mathematics of time. They built a machine to predict the future, not through magic, but through mechanical computation. It is, in a very real sense, the world's first analog computer, and its purpose was to model the behavior of time itself. Atomic clocks are now so precise that they can detect the time dilation caused by raising the clock a few centimeters. Modern optical lattice clocks, which trap atoms in a lattice of laser light and count their oscillations, are accurate to roughly 1 second over 15 billion years, longer than the current age of the universe. At this level of precision, the clocks become tools for measuring the shape of space-time itself. Two clocks placed at different heights will tick at measurably different rates, confirming Einstein's prediction that gravity affects time. These instruments are so sensitive that they could potentially be used to detect underground cavities, mineral deposits, and even changes in the Earth's crust by measuring the gravitational variations that affect the flow of time. A clock that was built to measure time has become so good at its job that it can now measure gravity. And in doing so, it reveals that time and gravity are two aspects of the same thing. Time feels faster as you age, and the most widely discussed explanation is the proportional theory. When you are 5 years old, a single year represents 20% of your entire lived experience. It is vast, packed with novelty, and seems to last forever. When you are 50, a single year represents only 2% of your experience. It is a smaller fraction of the whole, and it seems to pass more quickly. Another theory focuses on novelty. In childhood, nearly everything is new. The brain processes and stores enormous amounts of information, creating dense, detailed memories that are later interpreted as having lasted a long time. In adulthood, routines become established, fewer things are novel, and the brain processes less new information per unit of time. The memories are thinner, less detailed, and when recalled, they feel shorter. Neither theory is fully proven, but the experience is universal. Time accelerates as you age, not because the clocks speed up, but because the relationship between your mind and the passage of time changes with every year you live. Chronesthesia is the human ability to mentally travel through time, to vividly remember the past, and to imagine the future. It is not the same as simple memory. Chronesthesia involves projecting yourself into a different moment, experiencing it from the inside, feeling the emotions and sensations of a time that is not now. When you remember your 10th birthday, you are not merely retrieving a fact. You are reconstructing an experience, placing yourself back inside it, seeing through the eyes of the person you were. When you imagine next summer, you are projecting forward, constructing a scene that does not yet exist, populating it with sensations and expectations. This capacity appears to be unique to humans and possibly a small number of other species. It requires a specific neural architecture, including the hippocampus, the prefrontal cortex, and the default mode network. Chronesthesia is the closest thing to time travel that every human being does, every day, without any machine at all. Déjà vu, the feeling that you have already experienced the present moment, may be caused by a brief timing error in the brain. One theory suggests that the sensation of familiarity, which normally fires after the conscious experience of an event, occasionally fires before it or simultaneously with it. The result is that the present moment feels like a memory, even though it is happening for the first time. Another theory involves the hippocampus, which is responsible for both memory formation and spatial navigation. A new environment that shares features with a previously visited one may trigger a partial match in the hippocampus, producing a feeling of recognition without a specific memory to attach it to. Déjà vu is common, experienced by roughly 60 to 70% of people at some point. It is brief, usually lasting only seconds, and it is harmless. But it is a reminder that the brain's sense of time, its ability to distinguish past from present, is a construction, and constructions can occasionally misfire. Time perception changes under stress. During extreme danger, seconds can feel like minutes. People who survive car accidents, falls, and violent encounters frequently report that time slowed down, that they could see details they would normally miss, that the world moved in slow motion. The brain is not actually slowing time. It is sampling the environment at a higher rate, recruiting additional neural resources to process threat-related information as quickly as possible. This creates a denser record of the experience. When that record is later recalled, the density is interpreted as duration. More detail means more perceived time. The effect is driven by adrenaline and by the brain's threat detection systems. It is a survival mechanism. Our ancestors who could process danger quickly had a better chance of surviving it. The brain's response was not to give them more time, but to give them more awareness within the time they had. Isolated from all external cues, sunlight, clocks, social schedules, temperature changes, the human body settles into a natural circadian rhythm of roughly 24 hours and 11 minutes. This has been demonstrated in experiments where volunteers live in underground bunkers or windowless rooms for weeks at a time, with no way of knowing what time it is outside. Without the daily reset provided by morning light, the internal clock drifts slightly longer than a solar day, causing the subject's sleep-wake cycle to gradually shift. This internal clock is governed by a cluster of roughly 20,000 neurons in the hypothalamus called the suprachiasmatic nucleus, which responds to light signals from the retina. The fact that the internal rhythm is close to but not exactly 24 hours suggests that the circadian clock evolved to be entrained by external light, resetting itself each morning. Without that reset, you would drift through time at your own pace, living days that are 11 minutes longer than the world outside. The speed at which time passes is always experienced as normal by the person experiencing it. You can never feel your own time running slow. If you were aboard a spacecraft traveling at 99% of the speed of light, time would pass at roughly 1/7 of the rate experienced by someone on Earth. But you would not notice anything unusual. Your heartbeat would feel normal. Your thoughts would flow at their usual pace. A cup of tea would cool at the expected rate. Every internal process, every perception, every sensation would feel perfectly ordinary. Only when you compared your clock with an external clock, one that had not been traveling with you, would you discover the discrepancy. Time dilation is invisible from the inside. It can only be detected from the outside. This is one of the reasons it took so long to discover. The universe hides its deepest secrets inside the experience of normality. Einstein and the French mathematician Henri Poincaré independently worked on the problem of synchronizing distant clocks, and this practical problem of railway timekeeping contributed to the conceptual breakthrough that led to special relativity. In the late 19th century, the expansion of railways and telegraph networks made the synchronization of clocks across large distances an urgent practical problem. How do you ensure that the clock in Paris agrees with the clock in Berlin when it takes time for a signal to travel between them? Poincaré published papers on the philosophy of simultaneity and the conventions involved in defining what it means for two distant events to be simultaneous. Einstein, working independently, took this question further and reached a radical conclusion. There is no absolute simultaneity. Two events that appear simultaneous to one observer may not be simultaneous to another observer, moving at a different velocity. The problem of synchronizing railway clocks became, in Einstein's hands, a revolution in our understanding of time itself. The relativity of simultaneity means that there is no universal now. Two events that appear to happen at the same time for one observer may happen at different times for another observer moving at a different velocity. This is not an illusion or a measurement error. It is a fundamental feature of the structure of space-time. The present moment, which feels so solid and universal, is actually observer-dependent. Your now is not the same as the now of someone moving at a significant fraction of the speed of light relative to you. At everyday speeds, the differences are undetectable. But at relativistic speeds, the disagreement about what is happening now can span years, centuries, or millennia. There is no cosmic clock that everyone agrees on. There is no universal present moment that all observers share. Each observer carries their own present, their own past, their own future, and they do not align. In the film Interstellar, the time dilation experience near the black hole Gargantua was calculated using real physics by Kip Thorne, who served as the film's scientific consultant. On the water planet orbiting close to Gargantua, 1 hour corresponds to 7 years on Earth. This ratio requires the planet to be extraordinarily close to the event horizon of an extremely massive, rapidly spinning black hole. Thorne calculated that Gargantua would need to be roughly 100 million solar masses and spinning at very nearly the maximum rate permitted by general relativity. The physics is extreme but not impossible. The film took the mathematics seriously, and the depiction of time dilation, the crew returning to their ship to find that 23 years have passed in what felt like a few hours, is consistent with what general relativity predicts. Interstellar is fiction, but its treatment of time is among the most scientifically accurate ever put on screen. The novel Slaughterhouse-Five by Kurt Vonnegut presents time as the block universe. The protagonist, Billy Pilgrim, becomes unstuck in time and experiences all moments of his life simultaneously. He visits his birth, his death, his time as a prisoner of war, and mundane Tuesday afternoons in random order. The Tralfamadorians, the alien species who abduct him, see all of time at once and find the human obsession with the present moment baffling. They see each moment as fixed and eternal. Death is not an ending. It is simply a moment that is less pleasant than some others. Vonnegut wrote the novel in response to his own experience surviving the bombing of Dresden in 1945. The book's fractured chronology mirrors the way trauma disrupts the experience of time, making the past feel as vivid and as present as the moment you are in. It is both a war novel and a philosophical meditation on the nature of time, and its treatment of the block universe is more intuitive than any physics textbook. Time capsules are a form of one-way time travel. Someone in the present places an object or a message into a container and seals it, entrusting it to the future. Communication across time, offered without expectation of reply. The impulse behind a time capsule is the recognition that time will carry us away, that the people we are and the world we live in will become as remote as the ancient Egyptians are to us, and the desire to reach through that distance and say, "We were here. We thought about you. We hoped you were well." Many schools bury time capsules in their grounds, meant to be opened in 10 or 25 years. Children write letters to their future selves. They tuck in photographs, drawings, and small beloved objects. Then years pass, and one day someone digs up the capsule and holds in their hands the handwriting of who they once were. Time travel in this form requires no machines, no physics, no extraordinary technology. Just a box, a message, and the willingness to trust that the future exists. The oldest intentional time capsule still sealed is the Crypt of Civilization at Oglethorpe University in Atlanta, Georgia. It was sealed in 1940 and is scheduled to be opened in the year 8113, roughly 6,000 years from now. It contains microfilm of over 800 works of literature, recordings of voices and music, a set of Lincoln logs, a bottle of Budweiser beer, a Donald Duck toy, seeds, dental floss, and thousands of other objects chosen to represent daily life in the mid-20th century. The creators chose the year 8113 because in 1936, when the project was conceived, the Egyptian calendar was roughly 6,177 years old. They wanted to create a time capsule that would span an equivalent duration into the future. Someone in the 1940s looked forward 6,000 years and thought, I want the people who find this to know what our ordinary days were like. There is something almost unbearably human about that impulse. The certainty that time will erase us, and the quiet refusal to go without leaving a note. Stephen Hawking's A Brief. History of Time, published in 1988, sold over 25 million copies and became one of the best-selling popular science books ever written. It introduced millions of people to the ideas of space-time, black holes, the Big Bang, the arrow of time, and the possibility that time itself might have a beginning and an end. Hawking wrote the book while living with motor neuron disease, which had left him almost entirely paralyzed and able to communicate only through a speech-generating device. The book is remarkable not only for the clarity of its explanations, but for the calm, almost playful tone with which Hawking approaches some of the most profound questions in physics. He famously ended the book by saying that if we find the answer to why the universe exists, it would be the ultimate triumph of human reason, for then we would know the mind of God. The book did not answer the question of time, but it taught a generation to ask it, the arrow of time, the fact that time flows in one direction, from past to future, from order to disorder, from egg to omelette, but never back again, is one of the deepest puzzles in physics. The extraordinary thing is that most of the fundamental laws of physics are time symmetric. They work equally well in both directions. The equations of classical mechanics, of electromagnetism, of quantum mechanics do not distinguish between past and future. If you filmed a collision between two billiard balls and played the film backward, the backward version would look equally plausible. The laws of physics permit it. So why does time so clearly move in one direction? Why do we remember the past and not the future? Why do broken things not reassemble themselves? The answer, most physicists believe, lies not in the laws themselves, but in the conditions under which those laws operate. The arrow of time is not written into the rules. It is written into the starting conditions. And that distinction makes all the difference. The second law of thermodynamics states that entropy, roughly speaking a measure of disorder, tends to increase in a closed system over time. A tidy room drifts toward mess. A hot cup of tea cools to room temperature. Perfume released in a corner spreads until it fills the room evenly. These processes never spontaneously reverse. They could, in principle. There is no law preventing every molecule of perfume from spontaneously gathering back into the corner. But the probability is so vanishingly small that it would never happen in the lifetime of the universe. The arrow of time, in this view, is not a fundamental feature of the laws of physics. It is a statistical phenomenon. Time seems to flow forward because forward is the direction in which entropy increases. And entropy increases because there are vastly more disordered states than ordered ones. The universe began in an extraordinarily low entropy state, and it has been moving toward higher entropy ever since. Why it began that way is one of the great unanswered questions in cosmology. CPT symmetry is one of the deepest symmetries in physics. It states that the laws of physics remain the same if you simultaneously reverse three things. Charge, replacing every particle with its antiparticle. Parity, reflecting the universe in a mirror. And time, running the clock backward. Each of these reversals individually can produce differences. Some processes look different when viewed in a mirror. Some behave differently for particles and antiparticles. But when all three are reversed together, the physics is identical. This means that time reversal is deeply embedded in the structure of reality, not as a standalone symmetry, but as part of a threefold symmetry that connects time, space, and matter in a way that has been confirmed in every experiment ever conducted. CPT symmetry does not mean you can travel backward in time, but it means that the fundamental laws of the universe treat backward time as a legitimate possibility, provided you also swap matter for antimatter and flip the mirror. Time began with the Big Bang, roughly 13.8 billion years ago. Before the Big Bang, there was no time. This is not a poetic statement. It is, as best as current physics can tell, literally true. Time is a property of the universe, not something that exists independently of it. When the universe came into existence, time came into existence with it. The physicist Stephen Hawking described it this way: asking what happened before the Big Bang is like asking what is north of the North Pole. The question seems meaningful, but it contains a hidden error. There is no north of the North Pole because north is defined relative to that point. There is no before the Big Bang because before is defined within time, and time did not exist before the Big Bang. This is one of those ideas where our ordinary intuitions, shaped by a lifetime of living within time, simply fail us. The universe is under no obligation to be comprehensible to beings who live for 70 or 80 years on a small rock orbiting a medium-sized star. The observable universe is a time machine you can use by simply looking up. The further you look into space, the further you look into the past, because light takes time to travel. The moon shows you 1.3 seconds ago. The sun shows you 8 minutes ago. Jupiter shows you roughly 40 minutes ago. The nearest star shows you 4 years ago. The center of the Milky Way shows you 26,000 years ago. The Andromeda Galaxy shows you 2.5 million years ago. The most distant galaxies visible to the Hubble and James Webb Space Telescopes show you the universe as it was over 13 billion years ago, when the first stars were forming and the cosmos was still young. Every direction you look is a different depth of time. The sky is not a ceiling. It is a window into the history of everything. A neutron star's gravitational field is so strong that time on its surface runs measurably slower than time in empty space. A neutron star is the collapsed core of a dead, massive star, roughly the mass of the Sun compressed into a sphere only about 20 kilometers across. The density is so extreme that a teaspoon of neutron star material would weigh roughly 1 billion tons. At the surface, gravity is roughly 200 billion times stronger than gravity on Earth. Clocks on a neutron star would tick at roughly 70 to 80% of the rate of clocks, far from any gravitational influence. If you could stand on a neutron star and look outward, the universe around you would appear to be running fast. And if someone far away could watch you, you would appear to be moving in slow motion, living your life at a reduced speed, aging more slowly than everyone else. Neutron stars are real. They have been observed in enormous numbers, and the time dilation at their surfaces is not theoretical. It is a consequence of the same physics that makes your GPS work. Tachyons are hypothetical particles that travel faster than light. In the framework of special relativity, a particle that moves faster than light would, from the perspective of certain observers, appear to be traveling backward in time. The mathematics permits this. The Lorentz equations do not break down above the speed of light. They produce results that are strange, involving imaginary numbers and reversed causality, but they are mathematically consistent. However, no tachyon has ever been detected. If tachyons existed and could interact with ordinary matter, they would create causal paradoxes, effects preceding their causes, messages arriving before they were sent. Most physicists regard tachyons as a mathematical curiosity rather than a physical reality. But the fact that the equations of special relativity have a place for them, a slot in the mathematics where faster-than-light, backward-in-time particles could fit, is itself a fascinating feature of the theory. The chronovisor was a device allegedly built by an Italian Benedictine priest named Father Pellegrino Annetti in the 1960s. Annetti claimed that the chronovisor could view past events like a television, and that he had used it to witness the crucifixion of Christ and a performance of a lost play by the Roman playwright Quintus Ennius. He said the device worked by capturing residual electromagnetic radiation from past events, a concept that has no support in known physics. The story is almost certainly a hoax. A photograph Annetti claimed was taken of the crucifixion was later shown to closely resemble a wooden crucifix in a church in Perugia. No independent evidence of the chronovisor has ever been produced, but the story persists because it touches something deep in the human imagination. The desire to see the past as it actually was, to witness history with your own eyes, to confirm what really happened. The chronovisor is fiction. The longing behind it is entirely real. John Titor was an anonymous poster on internet forums in 2000 and 2001 who claimed to be a time traveler from the year 2036. He described being sent back in time by the United States military to retrieve an IBM 5100 computer, which he said was needed to debug legacy systems in the future. He described his time machine as a stationary mass temporal displacement unit installed in a 1967 Chevrolet Corvette, later transferred to a pickup truck. He made a number of predictions about the future, including a civil war in the United States and a nuclear exchange in 2015. None of his major predictions came true. The identity of John Titor has never been conclusively established, and the entire episode is widely regarded as an elaborate hoax. But it became one of the most discussed and analysed internet mysteries of the early 2000s, a modern myth about time travel that played out in real time across the emerging digital world. Retrocausality, the idea that the future can influence the past, is taken seriously by some interpretations of quantum mechanics. In certain quantum experiments, the outcome of a measurement appears to depend on a choice that has not yet been made. The delayed choice quantum eraser and Wheeler's delayed choice experiment both produce results that seem to suggest backward causation, though careful analysis shows that no usable information travels backward in time. The apparent retrocausality is visible only when results are compared after the fact. Nonetheless, some physicists, including Hugh Price and Yakir Aharonov, have argued that retrocausality should be considered a genuine feature of quantum mechanics, rather than an artifact of interpretation. If they are right, then causality at the quantum level is not a one-way street. Effects can precede their causes, provided the effect cannot be used to send a controllable signal into the past. Time at the smallest scales may not have a fixed direction. Wheeler's delayed choice experiment, first proposed by the physicist John Archibald Wheeler in 1978 and confirmed in laboratories multiple times since, demonstrates that a measurement made after a photon has passed through an apparatus can determine which path the photon took. In the experiment, a photon is sent toward a beam splitter that can either send it along one of two paths or allow it to interfere with itself along both paths simultaneously. The choice of whether to insert the second beam splitter, which determines whether interference occurs, can be made after the photon has already passed the first beam splitter. The photon's behavior at the first beam splitter appears to depend on a decision that had not yet been made when the photon arrived. Wheeler himself described this by saying that the past has no existence except as it is recorded in the present. The experiment does not allow messages to be sent into the past, but it blurs the boundary between past and future in a way that no classical physics experiment ever could. The black hole information paradox asks whether information that falls into a black hole is destroyed forever or preserved somehow. According to general relativity, anything that crosses the event horizon is lost to the outside universe. But according to quantum mechanics, information cannot be destroyed. It can be scrambled, encoded, and hidden, but it must be conserved. These two principles contradict each other at the event horizon, and resolving the contradiction is one of the most important open problems in theoretical physics. Stephen Hawking showed in 1974 that black holes emit radiation and eventually evaporate. If a black hole evaporates completely, what happens to the information it swallowed? Is it released in the radiation? Is it encoded on the event horizon? Is it transferred to another universe? The answer may require a theory of quantum gravity, and finding that answer may reveal something fundamental about the relationship between time and information. Time crystals are structures that repeat in time rather than in space. First theorized by the Nobel laureate Frank Wilczek in 2012 and created in laboratories in 2017, time crystals are systems whose lowest energy state involves periodic motion. Their atoms oscillate in a repeating pattern without consuming energy, like a clock that ticks forever without being wound. This is a new state of matter, distinct from solids, liquids, gases, and plasma. Time crystals do not violate the conservation of energy because they are already in their ground state. They cannot be used to extract useful work. But they demonstrate that the symmetry of time, the assumption that the laws of physics are the same at every moment, can be spontaneously broken, just as the symmetry of space is broken when atoms arrange themselves into a crystal lattice. Time crystals are a reminder that time is not merely a backdrop against which events happen. It is a dimension in which structure can form. The concept of imaginary time proposed by Stephen Hawking treats time as a mathematical dimension similar to space. In ordinary physics, time is distinguished from space by a minus sign in the equations of space-time geometry. Imaginary time replaces this minus sign by multiplying time by the square root of -1, converting it into a dimension that behaves mathematically like a spatial dimension. In this framework, the distinction between time and space dissolves. The universe becomes a four-dimensional surface with no boundary and no edge, like the surface of a sphere but in 4 dimensions. There is no beginning. There is no singularity at the Big Bang. Time simply curves back on itself, the way the surface of the Earth curves without having an edge. Hawking used imaginary time to propose the no-boundary condition, a model of the universe that requires no special starting conditions and no moment of creation. The universe simply is, a closed, self-contained structure in imaginary time. Whether imaginary time is a mathematical trick or a description of deeper reality is still debated. Gravitational time dilation means that your feet age slightly slower than your head, because your feet are closer to the center of the Earth and experience a fractionally stronger gravitational field. The difference over a human lifetime is roughly 90 billionths of a second. You would never notice it. No medical instrument could detect it, but the most precise clocks in the world can measure it, and they confirm that it is real. Your body is not aging uniformly. The top of you and the bottom of you are moving through time at different rates. It is an absurdly small difference, but it is a genuine one, and it is a consequence of the same physics that governs the time dilation near black holes and neutron stars. The universe applies its rules everywhere, at every scale, without exception. If you could somehow survive near the event horizon of the supermassive black hole at the center of the Milky Way, Sagittarius a star, you could watch the entire future of the universe unfold in front of you. Time for you would slow almost to a stop relative to the rest of the cosmos. While you experienced minutes or hours, billions of years would pass outside. Stars would be born and die. Galaxies would collide and merge. The universe would expand and cool and darken. You would watch it all from your vantage point at the edge of the abyss, a spectator at the end of everything, suspended in a moment that the rest of the universe had long since left behind. You could not communicate what you saw. You could not return, but you would have witnessed the full arc of cosmic history compressed into a single, endless afternoon. It is the most extreme form of time travel that the laws of physics permit, and the black hole is real. It is there right now, 26,000 light-years away, in the dark heart of the galaxy. The light cone is a concept from relativity that defines which events in space-time can influence each other. Your future light cone contains every event you could possibly reach or affect, given that no signal can travel faster than light. Your past light cone contains every event that could possibly have influenced you. Everything outside both cones is causally disconnected from you. It cannot affect you. You cannot affect it. The light cone is the boundary of your causal universe, the edge of what is real to you in the deepest physical sense. Time travel, if it were possible, would mean crossing from one light cone to another, connecting events that the geometry of space-time says should be forever separate. This is why time travel into the past is so problematic. It is not just about building a machine. It is about violating the causal structure of the universe itself. Time dilation is not symmetric in practice. In the twin paradox, the twin who stays on Earth and the twin who travels at near-light speed do not have equivalent experiences. The traveling twin accelerates, decelerates, turns around, accelerates again, and decelerates to stop. The stay-at-home twin does none of this. It is the acceleration that breaks the symmetry and determines who ages less. This asymmetry is what makes forward time travel real, and not merely a matter of perspective. The traveling twin has objectively, physically, measurably experienced less time. It is not a trick of clocks or a difference in point of view. It is a genuine difference in the amount of time that has passed for each person. The universe keeps count, and the count is not the same for everyone. Some physicists believe that time is not fundamental but emergent. It arises from deeper quantum processes the way temperature arises from the motion of molecules. No individual molecule has a temperature. Temperature is a statistical property of large collections of molecules. In the same way, no individual quantum event may have a time. Time may be a statistical property that emerges when enough quantum events are considered together. This idea appears in several approaches to quantum gravity, including loop quantum gravity, and certain interpretations of the Wheeler-DeWitt equation, which describes the quantum state of the universe and, strikingly, contains no time variable at all. If time is emergent, then at the deepest level of reality, there is no past, no future, no duration. There is only the structure from which the experience of time arises. The ticking of your clock, the beating of your heart, the feeling of one moment following another. All of it would be an extraordinarily convincing appearance, produced by something that has no time in it at all. The problem of time in quantum gravity is the fact that the most promising equations for unifying quantum mechanics and general relativity do not contain time as a variable. The Wheeler-DeWitt equation, formulated in the 1960s, describes the quantum state of the entire universe. But the equation is timeless. It describes a static state, not an evolving one. There is no t in the equation, no clock, no before or after. The universe, according to this equation, simply is. The challenge for physicists is to explain how the experience of time, the sense of change and flow and sequence that is so fundamental to human existence, emerges from an equation that contains none of it. This is not a minor technical problem. It is one of the central difficulties in the search for a theory of everything. The universe appears to be running on an engine that has no concept of time, and yet, here we are experiencing time with every breath. Carlo Rovelli, one of the founders of loop quantum gravity, has argued that time does not exist at the fundamental level. In his view, the equations of quantum gravity describe relationships between physical quantities, not the evolution of those quantities through time. Time, in Rovelli's framework, is not a stage on which events happen. It is a perspective, a way of organizing relationships between things. The sensation of time passing is produced by our position within the universe, by the fact that we are small systems interacting with a vast environment, and by the increase of entropy that gives those interactions a direction. If Rovelli is right, then time is like the color of a sunset. It is real in the sense that we genuinely experience it. But it is not a fundamental feature of the universe. It is a product of how we interact with a reality that is, at its deepest level, timeless. Julian Barber, a British physicist who has spent decades working outside the mainstream academic establishment, has proposed that the universe is a collection of nows, each one a complete configuration of every particle. In Barber's picture, there is no flowing river of time carrying us from one moment to the next. There are only configurations, static arrangements of matter, each one complete in itself. The sensation of time passing is created by the relationships between these configurations. Some configurations contain structures that look like records of other configurations, brains with memories, fossils in rock, light arriving from distant stars. These records create the illusion of a history, of a sequence of events leading from past to present. But in Barber's framework, each configuration is equally real, equally present, and the flow of time is a story we tell ourselves based on the evidence encoded in the configuration we happen to inhabit. Time, in this view, is the grandest illusion of all. Not false, but not fundamental. Every atom in your body was forged in the heart of a star that exploded billions of years ago. The carbon in your bones, the iron in your blood, the calcium in your teeth, the oxygen in your lungs. All of it was produced by nuclear fusion inside massive stars that lived and died long before the sun was born. When those stars exploded as supernovae, they scattered their contents across space. Those elements drifted through interstellar clouds for millions of years, before gravity gathered them into a new solar system, a new planet, and eventually a new body. You are made of material that has been traveling through time for nearly the entire history of the universe. The atoms in your left hand may have been forged in a different star from the atoms in your right. You are a temporary assembly of ancient matter, held together for a few decades by chemistry and electricity, before the atoms disperse and continue their journey through time without you. You are always traveling through time at a rate of 1 second per second. This is the most reliable, most democratic, and most inescapable form of time travel there is. It requires no spacecraft, no wormhole, no exotic matter. It is shared equally by every living thing on Earth. The bacterium dividing in a puddle and the whale crossing an ocean are both moving through time at the same rate. The president and the prisoner, the newborn and the centenarian. 1 second per second, without exception, without pause. You cannot speed it up. You cannot slow it down, not without moving very fast or sitting very close to something very massive. And even then, the difference is measured in milliseconds over a lifetime. For all practical purposes, we are all locked into the same relentless, beautiful, unstoppable forward motion through time. And there is something both humbling and comforting about that. We are all travelers. We are all moving through the same dimension, and none of us can stop. Time is the medium in which rest is possible, in which wounds heal and grief softens, and the things that feel impossibly large today grow smaller with the passage of days and weeks. Time is the ingredient in sleep. Without it, there is no rest, no dreaming, no waking, refreshed into a morning that is different from the evening before. Tonight, you will travel through roughly 8 hours of time without noticing it passing. You will enter a kind of temporal grace, a period in which the brain consolidates and repairs and processes, in which the body does the slow and important work of renewal. And you will emerge at the other end into a new day, carrying that rest like a gift from the hours of darkness. That is what time does when we allow it. When we stop fighting it, stop wishing it would move differently, and simply let it carry us. And that is where we will leave it tonight. 100 facts about time travel, from the atomic clocks on aeroplanes that proved Einstein right, to the muons that arrive at the ground because time stretches around their speed. From the GPS satellites that correct for time dilation every day, to the black holes where a few hours could be centuries. From the wormholes permitted by the equations, to the grandfather paradox that has no resolution. From the arrow of time that points in only one direction, to the physicists who believe that time itself may not exist at the deepest level of reality. From the oldest light in the universe, still traveling after 13.8 billion years, to the time capsule sealed in 1940 and waiting to be opened in the year 8113. From H.G. Wells, who invented the time machine with nothing but a pencil and an imagination, to Stephen Hawking, who sat alone with champagne waiting for guests from the future who never came. Time is the strangest thing we know. It bends, it stretches, it slows near massive objects and stops at the speed of light. It may not even be fundamental. It may be an illusion so perfect that the universe itself cannot tell the difference. But it is also the simplest thing we know. 1 second per second. One moment following the next. The quiet, steady, unstoppable current that carries everything, everywhere, always forward. You do not need to remember any of it. Time will still be here in the morning. It will still be bending around the earth, still stretching near the stars, still ticking at different rates in different places, still carrying you forward at exactly the pace you were always meant to travel. For now, there is nothing to solve, nothing to calculate, nothing to understand. Just rest. Let your breathing slow. Let your thoughts soften. Let time do what it has always done. Carry you gently through the dark, toward whatever is waiting on the other side. Thank you for spending this time with us. Sleep well. Good night.